right. Well, good morning. I got a few people here. I started the recording. My name is Harry Ricker. This is the June 1st edition of the Cosmology discussion group. Welcome, everybody. And I'm not in very good shape this morning. My voice is pretty hoarse. Hopefully it's not going to get worse. So I don't know how long my voice is going to give out last year before I get real much hoarser. So I've selected a topic for this morning that I was going to talk about, which was the quasi steady state cosmology. And that involves this book, A Different Approach to Cosmology by Hoyle, Burbidge, and Narlikar. Now, I covered in a previous meeting, I covered about the first half of the book. That was the discussion about, is cosmology religion? And I talked about some of the issues that are brought up in this book about the resistance of the mainstream to new ideas. So I'm going to try to talk about the latter half of the book and sort of finish that up. Okay, let's see here if I can do this correctly. I think I did it wrong. So I want to share. Can everybody hear me, or am I muted?
I can hear you.
Okay, can you see the presentation there visible?
No.
Oops.
There it is.
No presentation?
Oh, it is there now. Yeah.
I don't see it. I have to figure out a way for me to see it. Oops. Okay, can you guys see it?
Yeah. Yes.
If you could get rid of the left.
All right, I'm not going to. I haven't done this in a while. Last time I talked, I just talked off the top of my head. I did make a presentation, and I'm not sure what I'm doing here. I've got the presentation. I can't see it here. I'm not sure why I can't see it. I forget how that works. All right, so I'm going to go ahead and talk about quasi steady state cosmology, which I didn't really get to. QSSC is the abbreviation for it. It stands for quasi steady state cosmology. And that's a modification of the Hoyle-Bondi-Gold steady state cosmology from the late 1940s. And as I mentioned in a previous talk, they tried to kill the steady state theory. The mainstream decided they didn't like the idea, I guess, of having multiple cosmologies. That really, I think, didn't really go well with the idea that science had the answers to everything. To have a disagreement on different cosmologies wasn't really satisfactory to them. We talked about how Martin Ryle tried to kill the steady state theory with radio source counts, and that was in the 1950s. And so it kind of the steady state theory was sort of forced into oblivion by the mainstream. And so the quasi steady state cosmology is an attempt to remove those objections that supposedly they claim that it was refuted by observations And as I mentioned, those observations were primarily the radio source counts, which later proved to be erroneous. This version I'm going to talk about is in the book, A Different Approach to Cosmology by Hoyle, Burbridge, and Narlikar. Okay. So the objections to the steady state theory touched on that, apparently refuted by radio source counts based upon Ryle's Cambridge radio source surveys. And that was in the 1950s, and apparently inconsistent with the microwave background data. So when they discovered the CMB, everybody jumped on the idea that this was the answer. That this proved the existence of the Big Bang, and that kind of like, if you want to talk about the bandwagon effect in science, everybody jumped on that. That's the answer, and all the money went in that direction. Very little of it went to resources, to other ideas about cosmology or other theories of cosmology, which is kind of interesting in that in past history there was never really a theory of cosmology that was in science that was universally agreed upon. There was a lot of different ideas put forward prior to the 19th century in particular. Okay, what is there to like about the QSSC? Well, for those of you who don't like creation events, a beginning that sounds something like a religious idea, QSSC sort of has an idea that the universe is eternal or has existed for a very long time. Now, the primary thing about QSSC is that creation of matter is a physical process currently observable. And I think the currently observable part is the key point, as opposed to not observable past event inferred from the CMB. So I think the mainstream people would say, well, we can observe the cosmic microwave background, so we know what happened. But it's really just a lot of speculation. All they can observe is fluctuations in the cosmic microwave background. And from that, they infer, the physical process of creation according to their theory. I don't really find that to be particularly convincing. Doesn't invoke dark matter and dark energy. And I think that's kind of, if you look at it from my point of view, dark matter and dark energy are ad hocs. They're like, let's stick these things in there. And so what has kind of happened as a result of that is you could sort of say they become fudge factors, that because by adding different ideas in, you can eliminate observational evidence that refutes your theory. Okay. And now we're getting to the down to the point of the observational facts. So the QSSC is really based on trying to explain peculiar galaxies. And what a peculiar galaxy is a galaxy that doesn't really fit into the accepted models or the way of what people think a galaxy ought to be. And that's kind of in the beginning, the galaxies that were known were very simple, like the Andromeda spiral galaxy, and very straightforward elliptical galaxies, which are globular shaped galaxies. And there was nothing really particularly remarkable about them until they discovered, well, there's radio sources, elliptical galaxies, are associated with intense bright radio sources. And then they started discovering all these unusual aspects. Some galaxies have unusually bright nuclei. And over a period of time, the idea of what a galaxy is kind of became, how should I put it, not really what a normal galaxy should be, just sort of became, there were many different types of galaxies and galaxies exhibiting unusual effects. And these were not really considered in the Big Bang theory. And because that theory was, pretty well established, and it didn't really have room for these peculiar galaxies. Okay, so then we have the other thing where the QSSC tries to understand discordant redshifts rather than discount the observations. There's a big argument about.
You define discordant redshift, please?
I talked about that. That's where galaxy, two different objects are associated with each other on the sky, but they don't have different redshifts, so the distance can't be considered to be, the redshift can't be considered to be a measure of distance. You recall my discussion about that?
Yes, thank you.
Okay, there's a whole bunch of different aspects of this. There's the discordant redshift. There's also the fact that redshifts seem to be quantized. That's another problem. These issues aren't really brought into the mainstream theory. Then you have the provides an alternative to the black hole theory of active galaxy observations. So what this means is that galaxies were discovered that produce tremendous amounts of energy in their nuclei, which are the centers. And normal galaxies, as they're called, generally don't have any, they just don't have bright nuclei. They just look like, oh, there's a group of stars in the center. And so it was thought that they're just, galaxies are just these assemblages of stars. Okay, but then they started discovering, as I mentioned before, peculiar galaxies which have bright centers, radioactive centers, things that aren't really going correctly, according to the idea that galaxies are just collections of stars. So they came up with this idea that galaxies in their centers have black holes. Which is a theoretical hypothesis. It's not really based on an observation. It's a theoretical hypothesis, but they couldn't think of anything else to explain why this unusual activity is occurring there. And they have, then this is another interesting aspect, which is the mainstream has this idea that galaxies grow by eating other galaxies. That's kind of a bizarre idea, actually. So their idea now currently is that when a galaxy forms, they're small, and that the galaxies that we observe today, particularly like, for instance, M31, which is a close spiral galaxy, the reason they get big is that they eat other galaxies, kind of like they gobble them up. That's kind of interesting. Okay, here's an example of discordant redshifts. This is 7603. Here we have a galaxy on it's kind of on the upper right, the big thing, and then you have a little galaxy on the lower left, and the redshift, and then there are two quasars. Now, I don't know if you can see this. Can you see the arrows pointing to the quasars that are located in the tail that extends from the main galaxy to the satellite galaxy?
Yes, just about.
this is an example of a peculiar galaxy and discordant redshifts. So, the mainstream says, well, the redshifts are different, and so they're at different distances. But from this picture, it looks like that the satellite galaxy is connected to the larger galaxy, and then you have these quasars that are located in the tail. That's kind of an unusual configuration. Why would these quasars be located in the tail? And so that's an example of discordant redshift. So the mainstream would argue that these quasars located in the tail, they're just an accident. Here's NGC 3561. This is really an interesting case. It looks like the galaxy at the upper left top, which is an elliptical galaxy, is giving birth to these galaxies down at the bottom by some kind of ejection process where it's just push them out or giving birth to it, so to speak. Some people think that's what's happening is that or maybe it's an example of a galaxy split in half and to two different parts. And so what we're saying is one part giving birth to another part, or maybe it's splitting by mitosis or something like that. All right. So does everybody kind of understand what peculiar galaxies mean? That's an example of a peculiar galaxy, the one that I just showed you, and the other one prior to that. Those are peculiar galaxies. Okay, dissonant ideas adopted by the QSSC. Okay, the first point is Armbart Simeon, who's this Russian guy, in the 1950s came up with this idea of galaxies evolve and creation occurs by explosive cosmogony. Okay, the word cosmogony actually refers to the creation. Cosmology doesn't really refer to how things are created. Cosmology refers to what we see in the sky. It's not really a theory of creation. Cosmogony is the theory of creation. And this has kind of become obscured by the modern Big Bang science usage, that they talk about cosmology. And they don't really talk about cosmogony. Cosmogony means creative process. How are things created? How has the world come to be? That's cosmogony. And we don't hear that much about it because there's only, according to the mainstream, there's only one cosmogonical event. Can't even say that, I'm so hoarse. That's the Big Bang. So they push that off into the distant past, and we don't have any creation going on that we can observe in recent history. In other words, the cosmology occurred so long ago that we can only infer what happened. And QSSC tries to say, no, we can look at what's going on in these peculiar galaxies, and we should try to understand how creation occurs or cosmogonic processes take place by looking at these peculiar galaxies, because they're telling us how creation occurs. Okay, and how does this occur? Well, there's a couple of different ideas about that. I referred to the idea that there's a kind of like a lifelike process where a galaxy gives birth to another galaxy, as opposed to the mainstream idea which galaxies gobble each other up. which kind of is a bizarre idea in my opinion. So ARP and some other people, and I think I've talked about ARP before, have got this idea that galaxies evolved from quasars ejected from galaxies. So that would be why in the picture up here, you see there are galaxies in the tail. I mean, quasars are in the tail of this galaxy. So the idea is that the galaxy somehow is emitting these quasars. They use the term ejection. And then when these quasars, after they've been ejected out, they evolve into galaxies. Now, peculiarly enough, this is a well-accepted idea by mainstream that galaxies evolve from quasars. What they don't like is that the quasars come from other galaxies like seeds. You don't like that idea. Okay, and we have in QSS, kind of their argument is quasars evolve into near black holes that we observe as active nuclei in centers of galaxies. Now, why they use the term near black hole is kind of, they don't really explain why they use that term. I think the reason they're using that term is because it's become accepted terminology in astronomy that black holes exist in the centers of galaxies. And that explains why so much energy is being created in those locations. Their thesis is that the black hole is causing all this energy to be emitted, causing radio sources and that sort of thing. So I think they're using the term near black hole to sort of imply that it's kind of a black hole-like process that's going on in these galaxies. And it produces a lot of energy and looks like that there's a lot of matter being emitted from these locations, these near black holes, as they call them. Now, this has been measured, and one of the things they find out is that when they measure the velocity of the matter near the centers of galaxies, they find that it's coming out from the center, not going into the center as you would expect for a black hole. So that's kind of a contradiction. So the thesis that we have in QSSX is matter is created in the QSS thesis is that matter is created in these near black holes, these regions and centers of galaxies. And as I mentioned before, interacting galaxies are coming apart. They're not gobbling each other up. They're actually spreading apart. So the process is that might be that a galaxy produces a seed or a quasar, and that is forced out or ejected from the center of the galaxy, and then it leaves the vicinity of the galaxy and then appears as a quasar, which then evolves into a galaxy by the matter creation process. Okay. Some of the problems resolved by the QSSC hypothesis that galaxies are created from quasars, which are ejected. So we don't need, one of the advantages of this, we don't need the dark matter hypothesis. And you sort of say, well, because we're dealing with completely different physics. And so the physics of QSSC is talking about is matter is coming out from the centers of galaxies. So since matter is coming out from the centers of galaxies, it should be no surprise that that these rotation curves that we see in spiral galaxies don't agree with the hypothesis that galaxies are just these stable systems of rotating stars and nothing unusual is happening in them. Okay, it gives a theory for the
We
origin
got
of
very few money rappers. I ain't got one.
Excuse me, please mute. Please mute. Okay, so we have the other advantage of this is that it gives a theory for the origin of quasars and what quasars are, which mainstream theory doesn't really deal with this they don't really seem to have a clear-cut theory as to how quasars are created, what they are. They acknowledge that quasars are associated with the centers of galaxies, okay, and that it looks like galaxies evolved from quasars. That seems to be something that they acknowledge, but they don't really have a cogent theory for that. Okay, the discordant redshifts, the idea kind of is that this process of creation it involves a redshift change. In other words, perhaps there's an intense gravitational field in these quasars and in these discordant redshifts that shifts the spectral lines to the red. And that explains why the redshifts are not don't reflect the distance of the quasar or the galaxy object. And the other thing that's interesting about this is the inhomogeneous distribution of galaxies and clusters. If you believe in the Big Bang, there's really no reason why galaxies should form clusters and clusters of clusters. So you have this hierarchy of galaxies, galaxy pairs, then you have clusters of galaxies, and then you have clusters of galaxies, and you have these hierarchies. You have a very inhomogeneous distribution in the sky, which doesn't really agree with the Big Bang idea. There's no real reason why the assumption of the Big Bang and the mainstream is that the matter distribution of the universe is homogeneous, and the observations show that that's not the case. Okay, so moving on here, we don't have a whole lot of time. I want to try to finish this up in the next few minutes. Matter creation in QSSC. Now, there actually is a theory, and it's kind of hard to explain what their theory is, but they say that matter creation occurs with an energy conservation due to what Boyle calls a C field. C apparently means creation. And so he hypothesizes that the creation field, okay, there's a positive energy and a negative energy that's created. So there's conservation of energy and matter, okay, which it's kind of confusing. So what he says is that the positive matter remains inside the quasar or the black hole or the near black hole, if you want to call it that, and that the negative energy is ejected, okay, out beyond it, and it's this negative matter that's created is what we see in galaxies. That's what evolves into stars and what we see. The advantage of this theory is that we can try to infer what this process is by measurements and observation. Okay, so the idea is that we don't just create theories that say, this is our theory. What we try to do is we try to observe what's happening, make measurements, and then try to discover what the process is. The creation of particles of matters is conceptually due to the basic fabric of space-time. So his idea is that space-time kind of rips open, and then when space-time rips open, the matter is created by the C field. That's kind of obscure, I agree. Okay, so we'll finish off with some problems. Some people claim the QSSC doesn't explain the cosmic microwave background. So that's their big claim. They want to, the mainstream wants to kill this idea. They want to kill it completely. So they say, well, our model, the mainstream model, agrees perfectly with the data, and the QSSC model doesn't. Now, I find this kind of, disingenuous because they have all these fudge factors and ad hocs in the mainstream model. So given that it's got more ad hocs in it, it's got dark matter and dark energy and all these different parameters that they can adjust, it's easier for them to agree with the cosmic microwave background than it is for the QSSC, which doesn't have as many ad hocs in it. There's not really anybody really working on this other than I think the team is, you've got like three guys, Hoyle, Burbidge, and Narlikar, and I think both Hoyle and Burbidge have died. So Narlikar, I think, is the only one who's working on. They're not really getting any money, like most cosmologists today they're getting government money and applying for these government grants. And the way the grant system works is, you have somebody that evaluates your grant proposal. And if you want to do work on a theory that people on the grant proposal committee don't like, you're not going to get funding. So there's really not much work being done on this theory. So, if you're saying, well, this is not a particularly well-formed theory and it seems kind of vague, I mean, it's just like these three guys working on it. Okay, then I mentioned the Big Bang has many ad hocs. They're, you have the inflation, there was a disagreement with the observations and problems with it. So they invented inflation. You've got the dark matter that was added into it. There are people who can spend time working on all this stuff, getting government funding and doing all this stuff to work on alternative ideas like the QSSC. They don't really have as many people working on it. They don't have people in all these different universities and astronomy departments, working on grants to advance the ideas of an alternative cosmology. So we really can't expect it to be fairly well advanced as far as the theory is concerned and how it explains things. Okay, that's kind of the end of it. And we're coming up here. We got, I'm not sure how many minutes we got left. Okay, that's it. That's our 6 minutes left. I did want to mention a couple of things about it. I think there's some interesting parallels between what Vadimir's theory is saying and this QSS theory. And towards the end of their book, they do mention some problems that need to be addressed. And one of them is the angular momentum problem. It seems that mainstream cosmology cannot and does not deal with the angular momentum problem. Where does angular momentum come from? All right. Well, we don't have any comments or questions. So I'm not sure where you want to proceed or go to from here. I'm getting pretty hoarse.
Well, the angular momentum problem is dealt with in binary mechanics cosmology, and as far as I know, it's the only cosmology that deals with that problem.
You may be right. In QSSC, you can, of course, the process of the creation, okay? The way they do the creation is, so for instance, you might have two quasars that are created, and one would be rotating in one direction and the other would be rotating in the opposite direction, so that angular momentum would be conserved, as well as linear momentum, because they would be ejected in opposite directions. So in the QSS cosmology, which, as I mentioned, doesn't really deal with these issues in a lot of detail, you could assume that the angular momentum is conserved, because creation occurs such that you get opposite angular momentum from two quasars that are ejected.
Harry, would you say that the universe is static? You know, like that galaxies don't rush away and such.
You want my opinion?
Yeah.
Well, I don't know. You know, how do I know?
I don't know either.
I can think of a lot of different alternatives. They're not thinking of any different alternatives. They've only latched onto the universe is expanding because they interpret the redshift as being a motion away. So they're interpreting the redshift as a straightforward Doppler shift. And Doppler shift meaning if it's the red, that means it's moving away. So since it's Doppler shifted, that means that galaxies are moving away from us, and that means that the universe is expanding. That's kind of a simplistic way.
You know, you had mentioned discordant redshifts, which I had never heard of that term, but I was familiar with the concept. As far as
I mentioned that, I mentioned that in a previous talk on
okay.
If you maybe you would want to go back and look at that.
I wouldn't know where to go, but I've heard of the concept though. I mean, I just hadn't heard of it referred to that way. However, though, I think if there is an expansion, that it isn't a universal expansion. I don't think the whole universe could possibly expand, since I think it's infinite. I think it's a local expansion, though it's caused by maybe a cosmic explosion in a local area, even though very vast and astronomically, you know,
Well, there's the issue when you ask me the question. The issue is the mainstream has decided that the universe is expanding because that's the simplest explanation. That's essentially what it boils down to. That's the simplest explanation for the observations.
yeah.
And they're not really spending much time on alternative ideas. Is time changing? Maybe time is not progressing in a uniform manner, so that the rate of time evolution is changing. So the universe could be, quote, static, but time is changing. And so then that would cause a redshift too, but they're not interested in looking at that. Go ahead, Cornelius.
Yeah, I have a concept too on that, because my thought is that, you know, we are basically matter is congealing into universes, into galaxies and that, and getting condensed, and basically making stronger and deeper black holes, and if not black holes but gravity wells. And if we're going down into a gravity well, then certainly the rim, or the what's away from you, is going to look like it's like falling into a well. The top of the well looks like it's getting farther away. So you're actually not. It's not actually moving, but it's a relative thing. You're actually becoming deeply embedded into the well. So as matter is created or comes together, the black holes, the gravity wells get deeper. So it's just a perspective that, not that the universe does the contraction towards the bottom of the gravity well. Those are my thoughts on it. And I'm going to have to cut off because I do have to go to church. So
all right. Well, thank you for dropping
the recording later.
Okay, Jerry wants to make some comments here.
Oh yeah. Like in addition to the idea that the universe expands, one thing that Big Bang Theory sort of sidestep, I would say, is the idea of how galaxies rush away, like like galaxies that are really far away, they rush away faster than the velocity of light. And I guess they think it's possible because they think that space-time itself expands and that it carries with it all the mass and energy in the universe rather than the objects themselves actually rushing away, which I think is the truth.
So you think, well, okay, so we're at to the kind of the fundamental ideas. As I tried to point out, the basic idea hasn't really changed since the very first observations. When and I talked about this earlier, Slipper and Hugh Mason. Okay, those are the two names. They back around 1900, before World War One, made spectroscopic measurements of galaxies. Now you have to remember that this was back in the day when they didn't even know whether what galaxies were. They were called spiral galaxies were called spiral nebulae, and all the nebula were classed together. So you had gaseous nebulae, you had globular cluster nebulae, you had galaxies. These are basically in a telescope are kind of hazy white.
I guess that was before Hubble.
Right. Now, my point is that when they first made the measurements, astronomers basically, one of the main pursuits of astronomy is to measure spectral lines. And so they said, well, let's measure the spectral lines of these nebula. And so that's what they were doing. And Slipper and Hugh Mason were looking at galaxies. Now, they didn't really know that they were external galaxies at this time, and they measured the redshift. And so they said, well, they must be moving away from us at a very high velocity because their spectral lines are redshifted. And over time, they were finding more of these. And they'd say, well, this is the fastest nebula receding from us. As they measured more, they found that the redshifts were greater. And so they were talking about, this is the fastest moving nebula, that we've discovered so far. So, and that idea didn't really change.
Did they think this before Hubble, though?
Yes.
Oh, I didn't know that. I thought that Hubble was sort of, I thought that was what, that was when the redshift and the idea that the universe expands had started after Hubble. Maybe it was slightly before. I didn't realize that when they observed nebula that they had observed the redshift and predicted the galaxy's rush away.
Well, it's even commonly said that Hubble introduced that explanation for the redshift, and that was his primary thesis. But I would maintain that is not correct. There's a paper, I think it's jointly with Tolman, where he talks about the redshift, and he did a lot of further measurements on it and so on, relative to the distance away of these galaxies. But he said, look, there are some possible explanations. Explanation one is that it's a Doppler shift, and therefore it's actually moving away. These galaxies are moving away from it. But he says explanation number two is that it's a dissipation of energy, and it's nothing to do with that at all. So, in fact, Hubble, it's a misnomer to say Hubble's law says that everything is moving away. And the more it is redshifted, the further away it's moving, and the higher velocity and so on. That, if you like, is the Hubble-Lemaitre law. So it's explaining Hubble's observations according to one of his hypotheses. But he didn't by any means say that was the only hypothesis. In fact, he seemed to be rather doubtful about it.
Well, I think the point here is that mainstream, I think at this time, they were doing work on solving equations of general relativity. And they discovered that the equations were, as an engineer, I call them unstable. When you solve a differential equation in electrical engineering, and it becomes just a constantly increasing function of time, that says that the thing is going to burn up because it's consuming energy. More and more current, more and more voltage is going to explode, and that would be considered an unstable solution if you had a system that did that. Like if you designed a motor that started and then kept accelerating forever until it destroyed itself, that would be an unstable system. So they discovered that the universe was an unstable system, or not. Their solutions were unstable solutions. Okay, but then when they said, well, but these galaxies are receding from us, and that agrees with our equations that are unstable. And so that's when the idea that the universe is expanding, I think, kind of came together from in their mind.
Well, actually, Einstein in his I think it was written a year after the general relativity. It was the cosmological considerations of general relativity that he suggested that the universe seems unstable, that if it were static, that all the matter and energy would just conglomerate into, like, that they would rush into each other. He suggested that the universe is either expanding or contracting. And this was before Lemaitre had his idea that he sent to Einstein, and Einstein didn't think much of it at the time, but he later adapted it, which became the Big Bang Theory. But Einstein's conception of the universe expanding or contracting was much different than the idea that, the galaxies actually rush away at high velocities. I think he meant it in a much different way, I think, originally.
Mind you, there has been an evolution on the first conceptions, whoever originated them, that the redshift was principally a Doppler phenomenon, and therefore that objects were moving away from each other. That was the primary postulate. But now it's developed in the system that actually space itself is expanding. It's not merely that objects within the space are moving away from each other. Space is miraculously expanding. The very essence of the universe, its space, is actually expanding into nothingness. That's an evolution which wasn't there.
They actually even say space-time is expanding, which I don't think time can expand. I don't see how time and space, they have to exist together, because time can't exist without space. You can't imagine one without the other, or the absence of both of them, I think. I mean, like, that's unimaginable or impossible. However, though, with the idea that space-time expands, I mean, well, as far as actually, carrying the mass with it throughout space, I mean, I don't know. It just seems very out there.
If space-time were expanding, wouldn't that mean that it would take longer for light emitted by distant objects to reach the observer?
And I think that's what they suggest.
Modify the perhaps what the redshift actually is.
Well, if I'm understanding you correctly, I think that's what they suggest, which is what causes the extension of the maximum possible velocity, that the light could travel at further velocities because space itself is stretching. However, though, personally, I would say that space is an empty void, which physical phenomena occupies. Instead of it being like a mystical stretching and warping, like something physical. I don't think it's physical at all, personally.
You don't think space is physical?
Oh, no. That's just my personal view.
Well, it depends on what you mean by space.
What is your view of space?
Well, I'm not sure I want to get into that right away.
I thought we were going to discuss whether C is invariant. I mean, I don't know if we're going to get that later, or it just seems a fruitless endeavor.
I think we know the answer to that. I don't think that, and people just don't really want to agree that there is an answer. They'd rather talk about it endlessly.
There is one parallel between the two aspects, and you know, I know we're all inquisitive people, and we're not brainwashed, but if you say a thing often enough, it just becomes part of your unconscious. And C invariant, I mean, you know, I say it's a meaningless statement even, but that has been said so often that it's accepted. And the other thing is space expanding, a meaningless concept. If you say it often enough and the media is repeating it and all the scientists are repeating it and the academics are repeating it, you just accept it. You don't realize it's actually a meaningless concept.
I have a question for you, Ian. Would you accept the principle of relativity, that the objects exist and travel relative to each other, and that there isn't a universal frame? Well, you might suggest that there is a universal frame.
Well, that's a very long discussion, and we could spend some time on it, Harry, if he likes. But I mean, briefly, yes, both. I mean, I actually accept a type of analysis of a relativity principle, you know, following from Galileo for inertial frames. I do accept that. And I also accept, you know, an absolutivity of space as well. Now, you may say that's contradictory. No, I accept those two things together,
Oh, me as well.
actually. Oh, good, good.
Well, I have a further question though. Okay, you mentioned experiments where, okay, if the source of light, okay, that light travels independently of the source. However, if the observer is in motion, there is a discrepancy. Is that correct?
What do you mean discrepancy? A variation
Well, yeah, a
in the
variation, yes.
perceived.
That C
Yeah, of
is
course,
invariant
yes.
when the observer is in motion.
That's right. But see, you mentioned two other things, which I suppose are basically the same. I think you started your paper by saying, if you're on a moving object which is emitting light, is the motion of the object added to the speed of light, as say it would be in a cannon, you know, which is moving
Yeah.
along a distance and emits a cannonball. Um, and then yeah, so that in a way is parallel to the situation where the source moves, you know, the source is moving,
Yeah.
but the wave is actually captured in an ether. So the answer to those two questions, whether you have a ballistic system and the velocities are added, and also whether the perceived reception of the wave differs depending upon the speed of the source. The answer is no, it doesn't. However, as you just said, Jerry, again, we say, if the observer is moving, actually, Stefan is quite right. Harry said it, and some others said that he was right. Stefan expressed it very, very cogently. I mean, if you take the classical equations of Doppler shift and you apply it to the case of a moving observer, where the you know, the 1 plus v over c basically in the numerator. If the source is moving, it's in the denominator. And if you just work it out, that implies that the speed changes. I mean, it cannot be otherwise. It would be contradictory.
Well, I have a question though. If well, considering the principle of relativity, given that if that holds true, that how to determine which is in motion, like given the principle of relativity, if the observer is in motion, how to know that it really isn't the light source in motion, or both, or that they're just relative to each other? How to specifically say the light source is stationary and the observer is in motion, or vice versa?
See, that's where the medium comes in. I mean, Vladimir will talk about this, and I'll talk about the ether, and others will talk about it. So that's right. If there were no medium, well, then what you say is right. It would be totally reciprocal, and you'd have to develop some form of something like the special theory of relativity. But unfortunately for SRT, there's a medium which gives you a frame of reference. Just like if you had no medium, it would be impossible to have sound waves. You know, you evacuate a jar and you put a bell in it, you don't hear anything. But there is a medium. If you have a medium like a gas,
Such as the
well,
ether.
then you get a sound wave. But the only way to get that is to put a medium in, and therefore you have a frame of reference. Relative to the medium, whether the source moves or whether the object moves, there are quite two different
Well,
scenarios.
would you say that that light travels only like in a fixed way, only relative to the ether, though, or that it travels
Yeah,
relative
I
to
think
its?
some. Well, yeah, well, I wouldn't say it only travels relative to that, but yes, that is the most convenient way of looking at it, Jerry. I would say yes, because the medium is giving rise to its emanation. I mean, if you had no medium, there'd be no light. If you had no gas, there'd be no sound. So that's what gives rise to the thing. So yes, it's certainly most convenient
Well,
to consider it as moving relative.
I would also say that light is a very different phenomenon than sound, for instance, or other waves. Light isn't mechanical, you know, the way that it requires a physical medium. I mean, of course, according to mainstream, light doesn't need a medium at all. It can propagate through empty space. I mean, I don't know whether that's
Yeah,
the
that's the
truth.
error. That's the fundamental error, in my humble opinion.
I mean, the way that light works, I mean, like you can always zero in on a sound wave and see how fast it's traveling. But with light, I mean, light's ethereal. Like if you see light, if a light wave passing by, you can't detect it. Like it's almost as if it doesn't exist until it shines on something, or unless it's detected. I mean,
Well, you have different parameters, I would say, to detect it. So in the case of sound, you have things like pressure and density, and you might have the adiabatic constant as well. So things like that. Now, you say that's mechanical. I can understand that, but I don't understand light. Well, with light, you have the electric field, and you have the magnetic field, and in particular, you have the properties of those. Permittivity and the permit. So it's totally analogous. It's a bit harder to perceive those, but they operate in exactly the same way as the pressure and the density in the case of sound waves. There is another minor difference in that light is transverse and sound is longitudinal. But I mean, that's a detail. You can postulate longitudinal electromagnetic waves as well.
interesting thoughts.
Yeah, I think Stefan was very, very precise. I mean, in one sentence, he gave the answer to this. I'm sorry, there was a lot of interesting conversation. I don't claim to have had the time to go through all the details, and I certainly didn't have the time to correspond. But his thing just pointed out in one sentence, he had the answer.
Well, does frequency and wavelength automatically translate to velocity though? Because I mean, there's the Doppler effect with sound, though its velocity is the same. Even though light is different than sound, I think, as far as its constancy. Light travels at a definite velocity. However, though light, wherever you're at, however fast you're going, it's the same velocity no matter what, you know.
Well, that's the problem, Jerry. What you just said right there. It's
I
the
don't
same
mean to say it's the
velocity.
truth. It's just
Yeah.
that's what they say. I didn't mean to imply that.
Well, the problem is the problem is the words are kind of the words that are being used are ambiguous. The speed of light is constant. That's ambiguous. Constant relative to what?
To
Okay.
anything. I mean,
Well, if
that's
you
the way the
say
theory goes.
anything, if you
Whether
say,
it's
hold
moving at a
on,
constant velocity or accelerating.
they don't say anything. Okay. They don't say anything. They just say velocity of light is constant. Okay.
What if they're
The anything relative to anything is implied. So it's not explicit. That's the problem. Okay. So the velocity of light is constant, or you could say it's fixed relative to a particular frame of reference, but that frame of reference has to be unique. It can't be anything. It can only be constant relative to something.
Well, would you say that emission theory is correct and that velocities add in a linear way, or just that c isn't invariant in some other way?
Well, well, now you've asked a complicated question. I don't really understand what you're trying to say.
Well, the velocities add there's a velocity of like say a light source is in motion, and it emits a beam. Is the velocity that you receive of the light, is it the velocity of the source and the light itself added
So now
together?
you're talking. So now, as I understand it, you're talking about the emission theory, which,
Yeah.
okay. So now you've thrown in a different theory. So that theory doesn't have a lot of evidence to support it, and it's controversial. So I don't really subscribe, don't really agree with that that's correct. I think there's a lot of experimental evidence that shows that it's not correct.
Well,
And I think I cited some of that evidence. If the emission theory is correct, then the Sagnac experiment wouldn't show a difference between when the platform is motion and when it's at rest, because the velocity is the same relative to the mirrors.
well, if c isn't invariant though, like what are the mechanics of it? Like, how does it work? Like, at what level isn't it invariant? Like, according to velocity or however.
I'm not sure I understand your question. I,
Well, how to determine at what level it isn't invariant? Does it travel at a definite velocity? And what's the mechanics of understanding what velocity it travels at? If it isn't invariant, like what accounts for the difference?
okay, so you're confusing two things, in my opinion. The first one is um, to establish whether it is or is not, quote, invariant, whatever that means. Okay, it looks, I can't understand how you can explain Doppler shift if you say that it's invariant, because the Doppler shift says that there's a difference between when the observer is in motion and when the observer is at rest. The observer measures a difference in the received frequency and wavelength. And from that, you can infer the motion of the observer relative to the source. If the velocity of light is the same and invariant for everything, then how can this difference be detected?
Well, I guess they aren't actually measuring the velocity of light from the source. They're looking at the Doppler effect. So how to
The
determine how fast
Doppler
it actually
effect,
goes?
you don't understand. The Doppler effect is a result of the difference. And the difference is only going to be apparent if there is not an invariance of light velocity.
So you could calculate that and determine what velocity the light travels according to its source. Could you?
No, you're not paying attention to what's being said. If the velocity of light is invariant according to the Einsteinian idea, which isn't really very well defined, how does the Doppler effect arise? Because the velocity relative to the observer, according to Einstein, is the same whether the observer is moving or at rest. So the observer should never detect a difference between whether he's moving or not.
Do you see in all cases, in both cases, source or observer motion, the frequency changes? That's the Doppler principle. Okay. So how does that give you a speed which is independent of the source motion? Well, in that case, the source is moving, you have the frequency changes, but the wavelength changes in an inverse way. So the product of the two gives you the same speed. Now, in the case of the observer moving, you have the frequency changes as normal, but the wavelength remains constant. So how could the speed do anything other than change? Because the frequency is changing and the wavelength is not compensating for it.
I guess
Well,
I don't understand the
that was
mechanics of
the
the experiment.
argument that Cornelius and Stephen got into, and Cornelius sort of came up with two answers by using AI, and AI basically embraced both points of view from my point of view. But then in the first instance of the AI concluded that the velocity of light wasn't invariant, and then in another case, it concluded that it was invariant. But if you looked at it carefully, it sort of switched viewpoints by saying, well, from the relativity point of view, we get one answer, and from the other point of view, we get a different answer. So the AI wasn't really very helpful, in my opinion, because it wasn't really clear to me what assumptions it was using.
Well,
And then at the end of the day, it appeared to me that it was almost saying, or Cornelius might have put it in this way. He said, look, it doesn't matter what the experiments say. We're taking it as a postulate, and you must take it as such, and you must accept it because it gives us a universal parameter with which to define length. You know,
Yeah.
this seemed again a religious concept rather than a scientific concept.
Well, with the Sagnac effect experiments, I mean, like if you observe the way the system rotates, that one light wave has to sort of chase. This is what ChatGPT said. It has to chase one mirror while the other one has to, you know, like it's like moving towards it, so it doesn't have further to go. So that it's uneven distances, which could result in interference fringe shift. However, though, if the fringe shift, if they measure the fringe shift, the degree of it, if it's more than the predicted amount according to what they could calculate, it possibly does reveal that C isn't invariant, I would say.
I didn't really quite understand that. I think the Sadnek experiment is a classical experiment that shows that the Einstein postulate is false. But what they do is they say, well, it's not an inertial frame because Einstein's postulate doesn't say the speed of light is constant everywhere in every place. It just says so for inertial frames. And since no experiments are done in inertial frames, then they escape the fact that experiments disprove that postulate because no experiments can be done in an inertial frame. So it's just kind of a pointless argument.
It would seem a different story if it were a straight line type of motion. However, it rotates, and in that rotation, once it starts shifting around this way, this
Right, Jerry,
light wave has
let me stop
it has
you.
further to travel. It
Let
has
me
further to travel than the other one,
let
which
me
can
stop
result
you.
in the
This is
interference
nothing
fringe
more.
shift.
This is nothing more than the Doppler effect in a rotating platform. Do you
I disagree.
understand that? It's just the
I
Doppler.
don't see how the Doppler effect is relevant, personally.
Okay, so I explained this previous. We just went over this. The Doppler effect. There are two possibilities. Okay, in the Doppler effect, the speed of light is the same for the observer when the observer is moving and when the observer is not moving relative to the source. We know that there's a difference because there is a measurement that says there's a difference. But if the speed of light is invariant, then there can't be a difference. Do you understand that?
Well, the Doppler effect isn't looked for in the Sagnac experiments, though.
It's the same principle. The mirrors are moving and they're not moving.
They're moving, but they're rotating.
It doesn't make any
This light
difference.
wave
It's
compared
still
to this
motion.
light wave, it has further of a distance to travel, which can result in an interference fringe shift. If the degree of the fringe shift is more than the predicted amount caused by the rotation, then you might have something, I would say.
I don't think you understand what's going on.
What's going on?
Sorry to say, I don't think you understand the experiment. I explained this to you in the email. It's not a very complicated thing. The way science works is science.
Actually, it's quite complicated for most people.
All right. Well, let me just go into it. It's a question of same and difference. Science works by making comparisons, same and difference. Is this the same or is it different? You understand that idea?
Sure. Obviously.
Okay, in the case of the Sagnac effect, if the velocity of the light is the same, whether the platform is rotating or not, you don't measure a difference. Einstein claims that the speed of light is the same whether the platform is rotating or not rotating, but there's a difference. So it can't be, the velocity of light can't be the same because there's a difference when you do the measurement between rotating and non-rotating.
Well, the other day, Bob brought up a lot of experiments that were of moving sources that weren't rotating sources. I would maintain that with a rotating source, one light wave has further to travel than the other, resulting in an interference fringe shift. If the degree is more than that, then maybe C isn't invariant. However, though, Bob had mentioned these other experiments. Sorry to call you out, Bob, but he listed all these experiments that weren't verified, that they came up empty, that use a linear motion instead of rotating source.
Well, Bob is talking about experiments that deal with the emission theory of light. And so we're now talking about something different.
I think they were just trying to find out if C isn't invariant, whether it's emission theory or otherwise.
Well, I can't comment on that because I don't know what the experiments were trying to do.
Okay.
But the classic modern experiment is the Wang experiment, which is basically the Sagnac experiment along a straight line. And it's getting rid of the canard that you cannot even talk about this because in terms of special relativity, because it's a non-inertial frame. Even though Einstein did apply it to the difference in clock readings on the equator and the poles, the Sagnac experiment actually wouldn't work if either of these two things were true. If the emission, I'd say, if the emission theory were true, an additive effect, depending upon the ballistic movement of the source, well, then that would cancel out. You'd get no fringe shift. And similarly, if Einstein's generalized postulate that the speed of light remains constant independent of the speed of the observer, if that were true, the Sagnac experiment would give a zero shift as well. Now your expression, that the distance is changing, all right, is the second canard that I'm not saying it's incorrect, but it's the second canard that the mainstream put out for this thing. Oh, the distance changes. It doesn't contradict relativity. That's what the AI said. It's perfect in according to relativity, just the distance changes.
You can look and observe it. I've watched videos. I mean, you can look and you can see that one light wave has further to travel than the other.
So what the special theory of relativity says, that if you have a source there and if you have an observer moving towards it, the distance is changing. Or put it another way, suppose the source is moving and then the observer is moving as well. Okay, the distance is moving. In one case, if you're moving towards it, the distance is decreasing. If you're moving away, it's increasing. And yet they say, independent of the fact that in one case it has a lesser distance to travel, another case has a further distance to travel, you'll still measure the same speed. And as O'Reilly said, that not only seems to be nonsense, but actually is nonsense.
Well, actually, with interferometry, such as even the Michelson-Morley experiment, if it were designed just oblong, if it wasn't precisely accurate, they would receive an interference fringe shift if they were on equal distances. At least that's what ChatGPT says. And I know that's not always a reliable source, but
well, yeah, you can say that. It is true. I mean, the Sagnac, if you consider the light to be moving in the Earth's ether frame, let's just put it that way. Well, then there is a distance. When it's moving with the spin of the disk, it has further to travel before it gets back to the detector. And if it's moving against it, it has a shorter distance. That's right. You can look at it in that form. But if you're on the disk itself, there's a constant distance between the source and the the receptor. They're both on the fixed, nailed down to this disk. It's not changing. The distance isn't changing at all. And in order for the time taken by the two rays to be different, well, then the observed speed must be different. It's common sense.
When the system is stationary, they're absolutely the same distance. However, when it rotates, in its rotation, like the way that this sensor here, when it moves up there, it's very slightly further distance, and this one becomes closer when it shifts that way.
That's to you observing the disk from outside the disk. But were you spinning on the disk, you wouldn't say that. You'd say,
Well, the light wave itself.
Well,
Ian, what is your view of how the ether works with the propagation of light?
Now you're changing the argument, Jerry.
No. I mean,
he's got you.
He keeps
He got
mentioning,
you,
he
and then
keeps
you
mentioning
change
the
the.
ether.
Then you
Okay,
change the
let's
argument.
return. Let's return to it. I mean, I
Okay,
mentioned
the point
it
is.
seemed relevant
The
to me.
point is.
Sorry.
Okay, so the point is, according to Einstein, the velocity of the light on the platform is the same as the velocity of the light outside the platform.
Of course.
There's no difference. But when we spin the platform, there's a difference.
Yes.
So Einstein's can't be right. Einstein said that it has to be the same. We do the experiment, we find it's different.
I personally
Who's right?
don't know if C is invariant or if it isn't. However, though, I'm just open to looking at what's available to review.
Well, the problem is the word. The
critically
problem
looking at
is the word invariant. Invariant relative to what? The velocity of
How would
light
you define invariant, Harry? Because you keep
not
saying,
changing.
well, yes, that's the essential element, I would say.
Yeah, but that's kind of.
That it's
and then
always
you
the
could say,
same.
then you have the other same is constant. That also says not changing. Not changing according to what?
Constant is invariant.
Well, let's go back to the Doppler shift experiment. That when the source and the observer are at rest relative to each other, the guy measures the frequency. Okay. Then when the observer starts moving, the frequency is different. Why is it different?
I don't know if it is. I mean, like as far okay, I'll have to study up on as far as wavelength and frequency if it translates to velocity. I'll look up. I'll look that up.
Einstein would say that they can't be different. They have to be the same because the velocity of light is invariant.
Well, I disagree with Einstein on many fronts, of course.
Now you've changed your position. I just explained to you that
What?
You have to understand what the word invariant means. Invariant relative to the guy that's moving. So if the velocity
the source.
Okay, so the observer is at rest and he measures one result. And the observer starts moving, and he measures a different result. That says that the velocity of light's not invariant with respect to that observer.
Well, I would agree. If that is the truth, I would agree.
Well, don't you believe in the Doppler effect?
I believe in the Doppler effect, of course.
Okay, so they're different, right? So how do you explain their difference?
Velocity of light and Doppler effect.
So how do you explain their difference? All right, well, I should have been more careful there with the time. So are we moving towards a resolution of this issue or not? I don't really see a problem here as far as it looks to me like the experiments are pretty definitive. Even the simplest of experiments are very definitive about this.
Well, would you understand? Would you understand my sort of objections or
what objection? What's your objection? I don't understand.
Well, as I mentioned, the rotation of the frame.
Hold on. Well, that's no different than the Doppler effect. Rotation has nothing to do with it.
I don't see how the Doppler effect is relevant, though, with the Sagnac experiments.
It's measuring the motion of the platform versus the platform not moving.
The velocity of light, or seeing if it resolves an interference shift pattern. Fringe shift.
Well, same and different. Okay, you said the velocity of light is the same, whatever the motion of the observer. That's what invariance means. Okay, if it's the same, then there's no difference. You shouldn't be able to detect a difference. But the
When
difference
there's a
is
rotating
detected.
frame, though,
Hold on. A difference is detected when there ought not to be a difference. Do you not understand that?
where is that detected? What experiment?
Gary, you're just confusing things by
What
double talk.
experiment has it been detected when
We
there
were
is
talking about two experiments, the Doppler shift experiment and the Sagnac experiment.
which Doppler shift experiment?
There are tons of them. It's a well-known established fact.
Well, with Sagnac experiments, they aren't looking at the Doppler shift though. They aren't looking at the Doppler effect.
It is a form of Doppler effect. That's the point I've been explaining to you, which you don't quite want to
Well,
understand.
even if it is the
I mean,
rotating
Ian explained it
system,
to you.
one light wave has further to travel. Given that once it moves up, like okay, it's here, and then when it
But
rotates,
according to
then it's
Einstein,
there,
it doesn't
and then
matter
this
whether
one
light
moves to
has further
there.
to travel
That
or
light has
not.
shorter to travel than that light.
But according to
You're
Einstein, that makes no difference. Einstein then tries to say, well,
that
because
was
of
before
length,
Einstein.
hold on. Einstein says because of length contraction, the distance cancels out and they're the same.
Well, I
Don't
don't
you
believe in
get
length
that?
contraction.
Well, now you're just arguing for
But
the
what
sake
you're
of
doing
arguing.
is you're giving the classic, maybe unbeknownst to you, but you're giving the classic excuses which the mainstream gives. So in other words, I'm not encouraging you to use this AI because I think there's too much of it. But if you put in one sentence and said, look, the Sagnac experiment unambiguously shows that there's a difference and that there's a fringe shift. And yet, if the speed is constant to an observer on the disk, it should be zero. So this contradicts the special theory of relativity. Well, I can guarantee that one of the AI platforms, whoever it is, will come up and say there are two reasons for that. One is that it's an invalid experiment because you cannot do it on a non-inertial frame. Now, we can dismiss that because the Wang experiment does it in a roughly inertial frame. And anyway, you can divide the thing into infinitesimal elements, which are inertial. The other excuse it gives is it says, oh yeah, it doesn't contradict relativity because the distance is changing, as you've just said. You know, in one case it's moving towards, in one case it's moving away. Now, the fallacy is that to an observer on the disk, the distance is not changing. The distance between the source of light and the receptor remains constant. It's on an immovable hard disk. It's nailed down to the disk. The distance isn't changing at all.
I would agree.
And okay, so if you look at it from his point of view, and you got a fringe shift. How can that happen other than that the perceived speed is changing?
Okay, okay. It's a managed system. It's all relative to each other. Once it starts rotating, though, the velocity of light acts of its own accord. Okay, if there are two people to throw a ball at the reflector at the same velocity, like one that way and one that way, one would have a shorter distance. Would you agree that they're uneven distances, though?
That's got nothing to
It
do with
depends
it.
from
That's
which
just an
frame.
irrelevant fact.
Okay, never mind.
You can do the analysis on both frames. Actually, it's quite simple. You know, we can. It's only simple algebra, and it's classical physics, and it's obvious. If you got a 14-year-old child who had some knowledge of algebra, and you just gave him this experiment and said, "Do the analysis," he would do it correctly. It's Newtonian or it's classical, and you can do it from the point of view of an observer on the disk, in which case you get the distance is the same and the speed is c plus or minus v. And you can do it from the point of view of a man in the laboratory who's stationary, and you find that the speed is light moving in the ether and that the distance changes, as you say. You can do it either way. But special theory of relativity cannot analyze this. It contradicts it. And you have to engage in some very special pleading to try to save relativity in in the light of this stark fact. I would
Well,
think.
I'm sure you realize I don't accept relativity. I mean, I don't always side with the mainstream, of course. I mean, usually the opposite. I mean, I don't know what else to say
Well, what do you
as
not
far as the
accept
system
in that?
rotating and there being uneven distances. There are clearly uneven distances.
You seem to accept, yeah, but you seem to accept a very fundamental principle of the commonly expressed special relativity, the reciprocity, that the speed of light is constant, and yet you don't accept relativity. So I don't know why.
Well,
You know,
I have
you're
a
accepting.
question. I have a question. When the light source is stationary, okay, when which way is it? When the light source is stationary, okay, when the light source is in motion and the observer is stationary, why is it invariant then and not the other way around, given the principle of relativity?
Yeah, well, but
Why
no,
the
given
difference?
the special relativity. I
The
object
principle of
to.
relativity by Galileo.
Yeah, you're moving. You're talking about Galilean or more general relativity, and okay, we can discuss that. But you know, people use the term relativity, and they're actually referring to special relativity. In Galilean relativity, there wouldn't be a reciprocity any more than there would be a reciprocity in air. You know, because there's air there, which is the frame of reference for the sound wave, and if the it's not just the relative speed between the source and the observer. It depends whether the source is moving relative to the air or whether the observer is moving relative to the air. You get a different result. Exactly the same in the case of light, and it's the ether or the medium, whatever you want to call it, which is the frame of reference there.
Yes, but you suggested that if the observer is in motion and the source is stationary, that C isn't invariant. Why is it invariant the other way though? It would seem that it would apply each way to me.
That's only if you accept the reciprocity of SRT. Now, when you say invariant, I prefer to say that when the observer is in motion, the speed observed by him will change. Now, when the observer is constant, is stationary, and the source is moving, well, then his measured speed will remain the same.
Why is that though?
Because
I mean, I personally don't understand. I'm honestly
well,
looking to understand.
it's fine. You're asking good questions, but you know it could keep on going forever. It's hard to explain because it's moving in a stationary. We're assuming the ether is stationary, by the way. If it moves, that's another complication. Where it's moving in a stationary medium, so therefore it doesn't change. There's nothing to carry it forward.
If the experiment wasn't done on Earth,
if it went outer space, the source has deposited, if you like. The source has deposited this disturbance in this fixed medium. So how could it change? Relative to an observer who's stationary relative to that. He's not moving towards it and he's not moving away from it. He's stationary in that medium.
You know the way that in outer space, if there are two spacecrafts approaching each other, you don't know which one is in motion or which one, one might, like the guy in the spaceship here might think, well, this guy's approaching me very fast. And the other one might think the same thing. They might be in relative motion. There's no way to say definitively. So if this experiment were done in outer space, how to determine if the source or the observer is in motion?
Well, I provisionally claim that there's no part of space which doesn't have an ether in it. And I think if you did it in outer space, there would still be a medium. And I think maybe Vladimir would probably agree.
Why would the ether, though, cause, when the observer's in motion, why would it cause the non-invariance, but when the source is in motion, cause the
Jim,
invariance?
let me stop you here. Did you not watch the presentation that Roger gave yesterday?
Well, I woke up late, so I didn't see it all.
All right. Well, the point is that Newton solved this problem by, he said, well, there's absolute space and time. So he solved this problem that you're on the horns of that you're struggling with.
Well, I agree there is absolute space and time.
Well, in which case your argument about being out in space and which one is moving to what is irrelevant, because according
that doesn't discount the principle of relativity set forth by Galileo, though. I wouldn't say.
Well, now you're confusing different things. Newton says there's absolute space and time, and so therefore I can make the measurement.
That
Einstein
doesn't mean
says
there's
there's
an
no
absolute
absolute
frame.
space. Hold on, stop.
Sorry.
Einstein says there's no absolute space and time, so therefore I can make any measurement I want. I can make any argument I want because there's no measurement way I can measure.
Wherever that you measure something, that's what you go by. And you can choose any point.
The point is Einstein says the speed of light is the same, whether the platform in the Sagnac experiment is rotating or it's not rotating. He says there can't be a difference between whether the platform is rotating or it's not rotating because the speed of light is, quote, invariant, according to your terminology. You can't detect a change because the speed of light's invariant, but we do detect a change.
I know. I've explained my view of why.
And why doesn't matter.
Sagnac in 1913 designed the experiment to test this very hypothesis, and he concluded that I have actually proved SRT to be incorrect. But he showed that. So what they came in with the two excuses, lame excuses that we were talking about. Why this experiment, which manifestly proves that there is a difference, they tried to dismiss it by introducing special pleading.
Do you understand this, Jerry?
I understand it very well in my view.
Okay.
As far as the system rotating, they're uneven distances. No, seriously. Do you understand they're uneven distances? Do you understand they're uneven distances?
Einstein says as his postulate that it doesn't matter whether the observer is moving or not. The velocity is the same. That's his postulate. I mean, don't you get that?
I understand what Einstein's postulates are, the first and second.
I don't think you do, because we're arguing about this, and then
I don't know if you understand what I'm trying to say. I don't know if you really understand, because
of course not. Obviously,
you would at least seem
the
to
way
think,
you're using
hey,
the word
maybe there's something
invariant
there.
is ambiguous. Okay, so I think we're wasting time. We should move on to another.
Maybe so. Sorry to disappoint everyone.
All right, I guess we don't have any other topics to discuss. Somehow we were talking about this court. We were talking about redshift, and then next thing, the idea is about redshift is that it's a Doppler shift. That was the original idea, and then they changed that to be that it's not really a Doppler shift; that it's expansion of the universe.
And I may have been slightly responsible for introducing the diversion or conversation, because to me, these are both dogmas which have been stated so frequently that people unthinkingly, have them in the back of their mind, even when they're questioning, like Jerry is questioning SRT, but he has this dogma of the invariance of C, and people have the dogma of the red shift being caused by a Doppler effect. They have that in the back of their mind because it's just been said so often.
Right, but that's where you get to the problem where that's not really what the cosmologists are saying. They're saying that the space is expanding over time, so that stretches out the wavelength. So redshift is not actually a Doppler effect.
Well, I don't know. First of all, it was a Doppler effect, so they hypothesized, between objects which were moving further apart. But now they're saying space itself is moving apart, and that is carrying these objects away from each other. And
essentially, the way of thinking about it is that the wavelength is dilating. What does dilate mean? It means that it's expanding. So when something dilates, it gets bigger. Okay, so the wavelength that's emitted, okay, as it's traveling through the universe, the space is expanding, and that dilates the wavelength because of the expansion of space. So as the wave travels along, the wavelength of the wave gets bigger and bigger and bigger. That's not the Doppler effect. The Doppler effect is due to the difference in the apparent speed of light.
Well, I mean, there's a classical Doppler effect and there's a relativistic Doppler effect. The latter is the one they use. They say the speed of light is constant. So when the wavelength stretches out, the frequency contracts, and the product of the two give you the constant speed of light. I mean, we don't know what would happen if space expanded. It seems such a nonsensical concept. But according to the classical principle, it would depend on whether the observer is, again, back to the original argument, the observer is moving or the source is moving. In this case, let's say you have a distant nebula as the source. Well, that's moving away. So
well, they would
if the
say it's
source is
moving
moving,
away because they would say it's moving away because the space is expanding between us and them. So because space is expanding, it looks like it's moving away. You got that?
right?
So
Yeah.
space is
Well,
getting
that's
bigger, it's dilating.
yeah. So that's like a neo-Doppler effect, or it's a relativistic Doppler effect. And in one of the comments there, somebody gave, it might have been Cornelis, I think he may have got it from AI, but he just quoted the relativistic equation for Doppler, which shows reciprocity. Now, I believe that equation is incorrect, but that's what they use nowadays. Yeah.
Okay,
seems
does
like
anybody else want to weigh in on this? I think James was going to.
it seems like cosmologists have refined the art of creating concepts which cannot be demonstrated in the laboratory.
I'm not really sure I would say it that way. Their claim would be that they take concepts that are developed in the laboratory and apply them to cosmology. So, for instance, they do experiments in accelerators and smash particles into each other, and then they sort of extrapolate that to the beginning and origin of the universe, which strikes me as it sounds reasonable, but how do you know? But you're extrapolating from one situation to another situation on the assumption that the laws of physics are the same for the two different cases.
I honestly have come to the conclusion that whether at the macro scale of cosmology or on the micro scale of atomic physics and so on, there must have been something in the water that all these scientists have been drinking. They've just gone, to such an extent that against basic Greek logic, fantasy, you could start postulating things that maybe they're unconsciously doing it because it's really so interesting to the public, and it's getting the more media time and more government funding and God knows what. But they've gone away from logic to such an extent that it's not really paralleled in other spheres of human endeavor, I think, or even other sciences. It's the most fantastic type of explanations that they're accepting. And it's at cosmology because you cannot duplicate it in the lab. That's correct. But it's also at the minuscule scale, and that cannot be observed either because it's by definition it's at the subatomic level.
Okay, I kind of want to make a little bit of a point here, and I'm not sure this is relevant to what you were saying, but part of the issue about what Narlikar and what Hoyle is saying is that we should be looking at the phenomenon in the universe to infer how things are created rather than looking at a particle accelerator and inferring how things are created. Do you see the difference there of what they're trying to advocate is a difference of approach?
Yeah. Yeah.
Is that what you were trying to get at, Jim?
Well, not exactly. I just think that some of the ideas which certain cosmologists seem to accept are so far from anything that can be demonstrated in the lab. In terms of the physics that we know. Does
Yes,
that make
but you
sense?
have a difference of opinion, as I was trying to explain, which is you have the dissident people who write this book. They're saying we should be looking to the phenomenon in the universe to understand laws of physics, as opposed to the traditional view, which is that we should extend the laws of physics that we've discovered in the laboratory to the universe as a whole. And those are the two different views. And the view that's currently accepted is that we extend the known laws in our laboratories to the universe as a whole. And that project seems to me to be questionable. Do you understand why? Okay, silence. There's a difference of it. So in other words, what it boils down to is Hoyle, the people who wrote this book would say, we shouldn't try to explain what's happening in the universe based on what we observe in particle accelerators, because particle accelerators is just a limited, very limited realm of experimentation that can be done.
Well, exactly. But particle accelerators are just one tiny area of what people are doing in laboratories.
Well, yes.
So this overemphasis on what appears to be, and by the way, the results are highly speculative. If you look at what they're doing in terms of analyzing collisions, highly speculative.
Well, a lot of what they're doing today is just mathematical paperwork. A lot of it in cosmology in particular, it's just I have a theory and it's all just mathematical speculation. And you sort of wonder, what's the basis of the mathematical speculation? Does it have any real contact with reality? At least in Hoyle, in his book here, he's trying to say, well, what we observe outside happening in the universe, that should be the basis for how we're creating theories and thinking about things. Which is,
well, the only thing that we know about what's going on outside in the universe is what we measure here and now. And so the dichotomy of what the astronomer taking images of one type or another wavelength of light is part of our laboratory here on Earth.
I'm not
in other
sure
words,
I understand what
I
you're
don't
trying
really
to
think
say.
there's a dichotomy.
Well, I'm not sure I understand what your point is. My point is I'm trying to make here is that there's a difference between what there's some cosmologists are trying to do is they're trying to explain what's happening in the universe, okay, not being completely constrained by what physics is defined as in the laboratory. So in other words, we think we know everything about physics because we've done experiments in our laboratories, but that may not be the entire full, complete story.
Yeah, and neither position is complete. What the cosmologists are saying or what the laboratory people are saying.
Well, what cosmologists in the mainstream try to do is they try to extrapolate nuclear physics and establish gravitational theory to cosmology. And what has happened is that they were pretty successful in astronomy with apparently explaining how stars work and nuclear processes in stars, but nobody's actually ever gone inside a star and measured what's really going on inside a star. So they managed to create theories that do apparently agree with what is observed, but they don't really know what's happening in stars. So that's,
And that's about the same as what nobody really knows what's going on inside a proton. At the accelerator data is simply analyzed by, we're going to say that a certain event occurred or a certain interaction of particles occurred if a series of events are detected over time after a collision in our accelerator. And so, that's highly speculative. And so I would say both are highly speculative. Both approaches.
I can't argue your point there. It's what mainstream science accepts on a consensus basis. And unfortunately, what they accept kind of as a consensus is a kind of an enforced consensus, since people who don't agree with the consensus approach don't get funding, and they lose their jobs. So there's a filtering effect that maintains the consensus, right? So then,
Yeah, I mean, getting back to the slightly conspiratorial way of looking at this, it's got great PR effect to say that we can do experiments here on Earth that will show you how the universe originated and what's happening in the vast recesses of the universe. So we construct CERN or something like that. Now, I was actually there on the day that they opened CERN in whatever it was, 2011, I think it was, and there were, when we were driving to the place, there were people with placards there saying, "CERN, ban CERN, close it. It's going to reproduce the Big Bang and is going to destroy the world." So these scientists in CERN and in these big particle accelerators have arrogated to themselves the position of gods, so they can do whatever they want, and they can create the universe, they can destroy the universe. So give us funding, government. Look what we can do. We're so powerful, and dare I say, it seems to be working.
Yeah, well,
bit cynical, but maybe near the truth.
Until the money runs out, I think. The money may run out. That seems to be an issue.
I don't know what they'll do then. They'll
all right. So I guess to finish up a little bit, does anybody have any questions about what I presented at the beginning, and any comments on that? What I was, and I'm trying to make this point.
Yeah, in your initial slides, you talked about a quasar account, I believe it was inconsistent with the cosmic background radiation. And I'm wondering what chain of thought could justify such a statement?
I'm not sure what you're referring to.
Well, I think
Well, if I understood it, you said a radio count, and that's exactly the same question as I had as well. So you talk
yes,
about these
yes,
radio
Ian,
bursts sort of being
correct.
consistent. I'd like more info on that. Is if that's what Jim means.
Yeah, that's what I meant. Excuse me, you clarified that well, Ian. In other words, at the beginning of your presentation, Harry, which is very, very well done, by the way, thank you. That question arose in my mind. How in the world can these people say that this count is inconsistent with the cosmic microwave background radiation? I mean, what is the thinking there? What is the logic there? I would think that should be fleshed out rather than just
All right, that may be. I think we're talking about two different things. Right. The point I don't really like discussing this issue of the radio counts because it looks like that was a red herring and that what Ryle did was wrong. So he had this idea, back to get funding. Okay, well, we're going to discover, we can test models of the universe by counting radio sources and doing this survey. And the government says, sure, fine, here's some money to do that. And I think that may be what he was doing, what he was saying to the government to get money. We can prove whether this universal theory is correct or not by counting radio sources.
But how does that counting relate to the CMB?
No, it's not related to the CMB. It's different. That's the point.
Yeah.
I thought you said it was inconsistent with.
Yeah. How did it relate to being inconsistent with the steady state theory? The CMB, they also did. But no, this thing I think you said it was a separate bullet. How was that inconsistent, Harry?
Well, the steady state theory, I think, has a prediction about the expansion of the universe should adhere to a certain formula. And that formula is not necessarily the same as the Friedman models. And so what he did was he extrapolated based on this theory of expansion of the universe exists in the steady state theory. Ryle came up with a calculation of the distribution of radio sources relative to their brightness or the amount of power that they emanate. And so they made a calculation of how many of them we should find at a certain faintness on the sky. And he basically claimed that his measurements showed that there was a difference between that and what the steady state theory predicted. And so he claimed that falsified the steady state theory. Now, what's not clear to me about it is that people apparently don't accept this anymore because it's not really, there are apparently a lot of assumptions that went into this that really doesn't really look like they were really valid assumptions. So I've tried reading about it, and the more I read about it, the less I understand about it. So I only sort of try to present it from the point of view of this guy made a claim to disprove the steady state theory, but people don't necessarily agree with, it's not as accepted as it was in the 1950s in the light of later knowledge. Does that make sense to you? Apparently not.
No, I get the principle, but I don't have any of the details. I'd have to read the papers, I suppose, and go to a lot of details to see why it was inconsistent.
It's a kind of an arcane subject. And it goes to the idea that they thought that they could by looking at galaxies further and further away and measuring their brightness, that they by assuming that there is a distribution of brightness, galaxies have an average brightness. The further away we go, we can count how many of them we see with a given, and then based on the assumption of how bright they are, the further out you go, how many of them you should see based on your distribution of what the brightness is. Then they could say, well, the universe model is this or that. But that program, that was what Hubble tried to do. That program wasn't really very successful, and they sort of abandoned it in the 1950s because it involves a lot of assumptions about what is the brightness of a typical galaxy. You see what I'm saying? It turns out that that's not really an established thing that you can say a galaxy is this bright with a distribution around the brightness of. And, it turns out that there are these Seyfert galaxies that are brighter than they're supposed to be. Okay. And then there's galaxies that are not as bright as you would think. They're what are called dwarf galaxies, okay, which are small galaxies. So if you're looking out there, you don't know how big it is, how bright is it, because you don't really have a measure of its brightness because you don't have a measure of its distance. So that program doesn't really work, and they're not really working with it much anymore. Does that help you to understand? It's very complicated because it depends on what cosmological model you're using.
So the term quasi is used in what you described to mean what?
You're talking about quasi steady state model?
Yeah.
Well, I think it means it's not really the steady state model. It's sort of like the steady state model. I think that's what they mean, trying to have it mean. I'm just saying, if you want to know the details, my recommendation would be to read the book. And it's kind of a complicated book to read, but some parts of it are straightforward and easy to understand, like in the historical parts. Other parts where they get into the mathematics of the models, and all the mathematical details, it's very dense and very difficult to understand. I'm not sure that the real point of this is that there's a different approach to doing the science. And the difference approach is, as I was trying to explain that earlier, which is the approach that they're trying to go by is what's going on when we make an observation, when we see these peculiar galaxies. How can we explain these peculiar galaxies? Things that we wouldn't have expected to find. In other words, they had in their minds this idea of what a galaxy is. And then, so yeah, okay, we know what a galaxy is. And then Hult and Arp said, oh, wait a minute, here's a galaxy that doesn't fit our preconceived notion of what a galaxy is. So they call it a peculiar galaxy. Well, yeah, we could call it peculiar, except for the